I know this is the last presentation, so I want to try to stretch it out as long as possible. What I'll be talking about today is scaling semi-supervised production-grade ASR on 200 languages. Just a little bit context behind this. Well, I was thinking, what should I talk about on this conference, and what should I cover so people cannot, what is the pipeline idea, the information that I can give to the audience that they cannot find really well structured on Medium and on the internet, right? So I wanted to give some value. So in this talk, I'm gonna be covering how it looks like to scale ASR, and well, from self-supervised side, of course, in a production grade setting. So how do you make a product that will, help users, that will have some users and, scale it. A little about myself. I'm deep learning research lead at Assembly AI. I thought bragging about 4 stuff would be a great idea to do so. And yeah, here's my GitHub, LinkedIn, email, in case you want to give it a touch. So how the pipeline looks for a single language. Basically, we have some amount of steps that we have to cover to make a product that is, firstly, efficient. Secondly, it could be validated to use by users. And thirdly, you could reiterate over time. So you just, So you don't have a legacy code base and model structure that you won't use in the future. First thing is data acquisition, right? This is an important step even before doing the base model estimation. We're gonna cover base model and research and everything in the next steps as well. Data acquisition means that you have to decide what scale will you be fighting with, right? So if you're aiming for a language, let's say Hindi, where it's a really small amount of open source data, probably you're gonna have a hard time optimizing the model on a semi-supervised training stage. Second step is base model training. This is a step which is not actually practiced in many companies, as I see in academia and even from production side of pipeline as well. What this means is we're going to cover it a little deeper, of course, in the future slides, but as a cover information, you need base model to determine where you are today with some model that you decide to use and some data set that you could find as an MIT license, so you can use it commercially, or some data set that you have bought already. You need to cover these steps so the company knows what money and what resources they should invest now to get something, and how much should they spend afterwards, and what is expected. And how good can you do scaling, and what improvements can you make in the future. Third step is, well, what I call human backprop. What it means is you do a research, and you arrive at some conclusion, right? Okay, let's use this model, this amount of data, I don't know, these hyperparameters initially, which is a base model. Then you do testing, and you do tuning, and you repeat that, and probably 10, 20 times, because as much as experience you have, even if you don't use semi-supervised learning, but if you use semi-supervised learning, models are becoming really sensitive to certain hyperparameters. We have seen 13, 15% order rate differences across the languages with using different hyperparameters, which is really huge. So this part takes most of the time, actually. And one thing that makes a company actually better than others is not reliant on research. It's reliant on compute. We're gonna cover that as well. As a cover information on this as well, you need more compute to do many parallel experimentations, to fail faster, find many things much faster. So you can outrun other companies who are struggling with compute because they cannot do the same thing as fast as you can. And then you do optimization, because if you have an engineering team in the company, if you're in a middle stage, for instance, or even high stage company, late stage companies, there's probably an engineering team who will tell you, no, we cannot deploy this, because either it's not scalable, scales really slowly, takes up huge time to load, or it's not optimized, it's not efficient to run it because you will lose money at the end of the day. And yeah, many things, including accelerators and so on. And last is deployment, of course. This includes refactoring, packaging everything, and making it really smooth. So when you look at your code 6 months later, you won't be like, why did I write this, right? So it could be reused by other people as well. This is for a single language. This is for 200 languages, right? You do the same thing for 200 languages. Well, this is a little bit dramatic, of course, because some things are automated. For instance, base model, you choose once, and you do testing for one language, multiple languages, based on some range of hyperparameters that you already acquired in the first, let's say, 2-3 experiments. So you know what grid to search for, like, search for really edgy different things. You have some, base idea of what you should optimize. And yeah, it doesn't take 200x the time and energy and money and compute to do this, but it doesn't take like 2x as well. Like, it's a huge struggle to accomplish this. So let's cover what we can do as a company. How can we plan everything? What steps could we take to be able to scale, ASR on many languages? Yeah, component 1, data, of course. The first bullet point is kind of subjective. Many people might not, accept it, but this is the kind of conclusion after working for 5-6 years in deep learning I have arrived to. Like, model performance equals 50% of researchers' talent, 25 domain data, and 25 compute. Why is researchers' talent the top priority? I mean, you can see the big companies or the companies who are growing really well are investing a lot into getting really good researchers and keeping them, right? Why do they do this? It's not like, just a kind thing to do. That thing benefits both sides, right? Companies need really good researchers to scale and to think about some ideas that hasn't been covered yet. As an example, for instance, Facebook, was able to get the same word error rate on 1 hour data with Wave2Vec as deep speech was able to do with like 10,000 hours of data, right? Well, these metrics are not exactly as they should be, but it gives you an idea, right? So really good researchers came up with a pre-training idea and like model architecture that you could utilize. So when you fine-tune it on downstream task for ASR, it gives you the same accuracy as you could get on tens of thousands of hours of data like 4 years back. 25% domain data. Well, sometimes you arrive at a conclusion that data is data, and I mean, let's use everything we can. There are a lot of papers, some of them came out recently, that say that actually they show that all of your data is not really usable. Like probably around 30–40% of your data is garbage, even though you might have domain-specific data. What is the chance that you have domain-specific data for 200 languages? Very small, right? Probably you're using like open source data sets, which are either were initially academic, they're not noisy, they're not designed for production use. So your models will be pretty much learning really clean and, easy speech. So they won't be modeling the same thing as they will meet in the production. And 25% compute. As I mentioned earlier, you need the compute to do experiments really fast. So, and do things in parallel. So you can brute forcefully, with the help of some, of course, predictable things, such as like scientific experimentation and with like good researchers, you can achieve more by having more compute than other people. Yeah, most data sets are not domain specific and lead to lower performance, of course. And companies who have like much bigger amount of data, they will probably beat you if you don't think of anything else, right? Because if you take a really terrible model and you train it on a huge data set, it's kind of gonna do the same as really, really great model on really small amount of data set, right? And companies with extreme compute have better chance at getting better results. Well, we have seen all the papers from big companies, including like neural search and to like parallel experimentation on like predefined hyperparameters. What it gives you is, well, a normal thing that you encounter in your life. If you have bigger resources, you can do more failing, and you can do the human backprop well. Basically, it's your, you're a model, and experimentation is the data. So you optimize yourself what to do as much resources you have. It's always to hire annotators by yourself rather than by data or outsources. So if you have an experience with working with companies to acquire production-grade data for ASR, you have read an email with a price tag on it, and you thought like, this much for 100 hours of data, this is crazy, right? That's why making an annotation in-house, I mean, you don't have to sell to yourself with margins, right? So you take away all the commercial stuff that other companies are giving you on the price tag. So you can do it more efficiently in-house, and it will be cheaper, it will be faster, but it's like creating a new company in your company. So there's like management, logistics, you have to do some web stuff as well, because where are they gonna annotate all these things, right? And probably you can optimize many things during annotation when doing everything in-house. What we are looking for when acquiring the data. Domain-specific data set. This is the most important thing we have to look for sure. Well, if you don't have an access to domain-specific data set, you could do augmentation, right? And by augmentation, usually what a person means is, okay, let's do frequency masking, let's do time masking, and that will help the model to, learn better, be more robust, because you're doing some sort of augmentation, which is not a good idea, most probably. Time and frequency masking are the most popular augmentations for speech, as you can see in the papers and from the companies as well, from tutorials, from blog posts, so on. It's not really good for either type of models. We're going to cover that a couple of slides after, but why it's not a good idea is that when you're doing time masking, you're basically stripping out something, some part of the audio, right? So the model has to predict something which is not there. Well, it's good to force the model to have a better context and force it to model actually the language inside the speech. So if you have, I don't know, H and O, the model can learn, okay, this word probably is like hello. So it gives a higher competencies over the ELL, right? But what this leads to is your model will be hallucinating at the end of the day. And that's okay thing to do if you're not doing production, or if you're not using the models in production, because in production, models have to transcribe many things that are named entities. It's probably easy to do hallucination over some easy words that you can hear many times, right? But if you're predicting some, let's say, I don't know, name of the city or name of the person or address, hallucination is not a good thing to do there. And in addition to that, when you're doing the decoding, like language model rescoring as a later step, you won't have a good predictions initially to rescore, right? So the alpha betas that you're using to use models confidences and language models confidences, they're not gonna probably help you. Yeah. The component 2, the base model. Well, as I mentioned, I don't actually see, maybe that's my problem, but I don't see companies actually using base model approach. I know it's tricky. Some things are really hard to do from experimentation and research point of view, because, I mean, human nature is not designed for really harsh logical thinking. And sometimes you think, okay, I mean, deep learning is really intuitive, right? Maybe I could guess a couple of things, and maybe probably those things are gonna be really good to use later stage, or if it's gonna struggle us, we'll think of something else. That's a great thing to do if you're a solo researcher or if your company doesn't have to scale this service on many languages and with many important customers. But if you can do that, if you have to do that, you have to estimate your base model because of a couple of reasons. Firstly, you will be having a user life, and your colleague researchers will be having user life. Secondly, it's going to cost to the company much less because it will know where you're standing. It will be easier to predict what resources will you need, how big your team grow for the next, I don't know, like year and so on. And plus, you can take in calculations for data sets and so on and so on. The choosing base model is really hard. Well, it's terrible job to accomplish because, well, it's an initial stage, right? And you have to say, I'm betting on this model, and this will be really good based on experimentation, right? And probably we're going to be able to scale this. Well, it's taking huge responsibility, right? But, I mean, there are some hyperparameters that we can optimize, even by intuition. Well, firstly, model types: encoder, transformer, conformer, convolutions. Loss types like CPC, RNT. Well, let's cover only like mostly really popular losses and model types. Then number of parameters. Probably you have seen like we have trained 175 billion parameter NLP model as as a papers and so on and so on. You cannot really do that when you're doing an multi-language production ASR, because that's gonna struggle you in terms of scaling. You won't have the same margins because your cost of the services will be huge, and it will not be hard to reiterate because it's gonna take, I don't know, like 2 months on 8 A100s to train like a 2 billion parameter model. So it's about deciding what do you need and why you should go with some number of parameters. Maybe you could just say, let's have lower accuracy for now, but as we have some more customers, we can make the models bigger, we can add features, charge them more, and so on and so on. And learning rate and the scheduler and freezing, unfreezing, which was actually firstly pointed out in the Wave to Wake paper as a really important thing to do. So turns out that during semi-supervised learning, when you take the model and use it for downstream task, it's really sensitive how you update the weights. So if you use pre-trained weights somewhere and you have some randomly initialized weights somewhere, you probably don't want to have the randomly initialized part drive all the optimization, because it will do huge weight updates initially, and the weights in the upper model, which has already pre-trained weights, is going to disappear or change by huge steps. You don't want to do that. So it's important to know how to do unfreezing and freezing, and that's, of course, experimentation. And pre-training. In the same component, how to estimate the base model. Well, there are a couple of questions you could ask yourself, which will help you arrive to a conclusion, what to even experiment with, right? Firstly, a small data set is not really good for RNNT, transducer models. Why? Because they are, well, much better at modeling the language, like not speaking literally, but so if you have really small amount of data sets, transducers tend to overfit on the words that are in the training data set, and you will have really hard time predicting name entities during the inference and in production. And that's really terrible thing to happen because your company wants, your company wants to transcribe everything that other company is looking for, right? And probably those most important things are some named entities, right? Because of marketing, I don't know, like personal information reduction, so on, so on. ASR is a really complex task, right? It's not a, I would say it's like on the higher scale of complex tasks. But, I mean, in these scenarios when your task is really pretty complex, you can say that having more parameters will help network get better results, right? Probably you'll agree with me. But there's a thing to decide, and that this is not like exactly from engineering standpoint, right? If you're in a startup, going with high parameter network, as I mentioned earlier, is gonna cost your company a lot. So you have to decide, okay, should we like spend huge amount of money right now on scaling these huge models? And will that help us getting the customers in a time frame where we still have money, and then we can start thinking about optimization? Or, let's just start with smaller models because you didn't yet find product market fit, and you'll just go from there and make your product really much better with extra features and stuff, and not brag about word error rate, and you can do all the optimizations of accuracy later on. If you have small amount of data, self-supervised pre-training is the way to go, right? I mean, probably most of you have read or heard about the recent developments in ASR. And let's say Web2X, which is really pretty much the most popular self-supervised pre-training model. With Web2X, you can do huge pre-training on like unlabeled data set, and then you can use like 10 minutes of the specific language data set, and you can get pretty decent word error rate. Well, in terms of academia, right? For, if you have academic training set and if you have academic validation set, which is really crazy and which is really cool. So if this exists, why not using for production, right? And if you do use it, the models are really, really sensitive. As we mentioned earlier, how you update the weights and which weights do you update plays a huge role where models gonna converge later on. Okay, and after you ask this couple of questions to yourself and arrive to some conclusion, and you have initial idea, you do some experimentation, then you say, okay, this is my base model. Now I can search for a couple of parameters, and probably it's gonna make it better. That might be batch size, that might be learning rate, that might be freezing authorizing schedule, and so on. Yeah, component number 3. This is where companies are spending the most of the resources. So if you have the initial model, the base model, or let's say you have already deployed model, but you say after 6 months, okay, we have to reiterate this model because customers are saying that it's struggling at some, I don't know, identifying like named entities, let's say, right? So you have to make it better. How you do it is, again, probably I should trademark this one, but yeah, it's a human backprop, basically, the same cycle. So you actually tune something, you do some estimation. Probably it's struggling because, I don't know, like we don't have enough named entities in the language, right? Or maybe you can add extra loss, which is like named entity CTC loss, right? So named entity word loss, right? So you do the CTC, and then you calculate your named entity word error rate, and you do that, you add that as a coefficient, right? And you train the model, and you do evaluation. And actually, the human icon here is not by an accident. The evaluation should be done by metrics, objective metrics, but by subjective metrics as well. Why? Because word error rate and character error rate or word information loss is not everything that you need to say we should really deploy this model, right? Because it's really hard to identify if your model is better at really something really specific and small using these metrics. So what do you need here? You need to do subjective estimation, right? Look at the outputs, like eyeball them, I don't know, like that. Do difference checks. you need the subjective part of the evaluator as well to say, okay, yeah, this really specific thing is kind of fixed, so we'll probably okay to deploy this. Or it's not as good as we thought it was, and we have to do the tuning and training again. So yeah, this cycle is where the most of the resources are spent averagely, and as big as you have, like each component of this cycle, so bigger the better in this case as well. If you have huge resources to train the models, well, you can identify better ideas much faster than other companies because, well, you have a ton of GPUs. If you have like researchers who can evaluate, or for instance, or contractors who can evaluate the output subjectively, you can do the same. You can move fast forward. And you can say that the same for analyzing and tuning as well. Most important part here from researching standpoint is tuning, of course, which is a really hard thing to do. And like from personal standpoint, I feel like as more time I spend into deep learning, more I think that it's really, it's really hard to intuitively estimate what will be the outputs. Yeah, we have a really small time left because I don't really have a sense of time. Sorry for that. So we're gonna go for a couple of frames really quickly. This is TVT, train, validate, tune. Basically, like some companies say, no, okay, let's do a couple of training runs and let's just deploy it really quickly. And that's okay thing to do initially. But if you do want to make a huge steps during, as a researching company or as a production-oriented company, you do have to invest in this, of course, because you can't move really forward if you don't have many choices to choose from. Yeah, which model do I need? Just as a some medium story cover, we have transformers and conformers as best things to use pretty much right now as an encoding models, right? Transformers are really good at catching long dependencies. They are easy to pre-train and easy to fine-tune, and we have been using it for like some time already, and we actually know them really well at this point. But conformers are transformer plus like convolutional layers, right? And ASR, if you think by its sense, is actually a local problem because you're classifying each frame, right, as a probability of the characters. So you can use that local attention, which could be provided by convolutions, and you can boost that features by long-term dependencies with transformers. Self-supervision, MLM, contrastive, even adversarial losses. With self-supervised pre-training, you can make your models much more robust, for sure. How you can do that? You can take huge amount of data, which will be production level data, because you don't need them to be labeled, so you can crawl YouTube and so on with like MIT licensed videos and audios. And you can do pre-training on them, which will make the models weights much more robust. So when you do the fine-tuning on a not so robust data set, now, I mean, it's gonna compensate a little bit. Now, yeah, about losses. I'm covering the frames much quickly, as I mentioned, because we have small amount of time left. CTC and RNNT losses. Like personally, I'm a big fan of RNNT. If you have enough amount of data, like transducer is the way to go, of course. It's really elegant. It's really robust towards noises and like some adversarial things that you can see in your training during your fine-tuning. But it's easy to overfit RNNTs. It's harder to scale and optimize, which is the reason why CTC is better if you don't have all the hyperparameters optimized from engineering, research, and even business side, right? So if you have to do quickly, iterate quickly, probably you're gonna be better off with CTC because it's easier to optimize, it won't overfit, and it's easier and scalable to tune. The last part is optimization. Probably you can remember these logos, right? ONNX, TensorRT, and the last is torch neuron, which is like inferentia from AWS accelerator. Well, what are the differences in between these accelerator frameworks? TensorRT, which is called, like TensorRT runtime, Triton runtime. Well, TensorRT is really, really amazing accelerator. The problem is that you have to optimize it for specific model, specific input size, and specific hardware. Well, that takes out most of the most of the slowdowns that come from other accelerators, because you can predict the computational graph really well, and you can optimize the kernels, how to move the data in GPU so you're not restricted by speed of light, and how to compress and fuse the layers. So it's harder to optimize and harder to scale, but it's much faster than anything. ONNX is a little bit slower than TensorRT because you can use multiple backends, right? So you don't have entirely pre-computed computational graphs, so you can use CUDA and you can use TensorRT as a backend, right? So and you can have dynamic axes as well, so you can change batch size, change sequence length. These are kind of trade-off that ONNX gives you. If you don't need that extra 20% acceleration, you can use this. Torch neuron, which is like AWS Inferentia's compiler for the models, are, by the way, like really, really cool things to use. But the idea is that it's hard to estimate what you should be using from hardware standpoint, and how you can scale it. What I mean by this is you can use the infinite instances such as like multi-core, multi-threading. You can just take one model and make replicas over the TPU pods that Inferentia comes with. I'm not sure if it's legally the exact word I should use, TPUs, but optimize hardware. So it's kind of engineering and business standpoint as well. So what should I do? Like which Inferentia instance should I use for my model? So I know that it's harder to decide compared to other accelerators, but you'll be much better off probably by optimizing everything in advance and like investing a little time ahead, because then while you will be doing scaling in a long run, like let's say next year or 2 years, well, you'll pretty much know everything you have to know, and you will be knowing like what is the optimal things that I can use to increase the profit margin and keep that scaling easy. Actually, this is like last two slides. I wanted to talk about the deployment part as well, which is, I have an engineering background as well. So I'm really cautious about things to do in machine learning that will be deployed, because then it's not easy to sleep when you do some decisions that is gonna struggle engineering, right? So first thing first is open source library dependencies. It's easy to use open source libraries for experimentation and like initial deployments, but it's not a good idea to rely on high-level open source libraries, because they're gonna struggle you in the end. Because some things are gonna come off for sure that need a custom, custom paths. You have to do something really, really custom, and you'll have to write, extra 2,000 lines to just support that. But if you had used like PyTorch, for instance, in pure PyTorch, you could do the same for, like 20 lines, because it's a fundamental core library, like really low level in Python terms. Hardware choice. Some hardwares are really, really expensive, such as, let's say, A100s, but we should not be afraid of the price of GPU per hour. What we're looking forward to is cost-benefit ratio, right? Because let's say A100 comes with really high price, but you can do all the really amazing things. It has high VRAM. You can partition the GPU if you have small models, and you can replicate one model on many sub-GPUs. And plus, they are much faster, and they come with all the efficiencies, which if you calculate with those efficiencies, in a price perspective, they are not, I mean, they're pretty, efficient at the end of the day. Model optimization and software optimization choice. I like divide and conquer approach to code base, like deep learning code bases, which means that it's not a good idea to have like 1,000 line class or module and do the, everything in one instance. What I always vouch for is, okay, we have this inference, right, which consists of some pre-processing, some neural network things, some decoding things, and some post-processing things, right? Okay, let's just package all these things and let's try to optimize how many and which workers should we use for each other. Because there are some things probably that's not gonna need to be replicated because they take a really small amount of time to accomplish their job. So you don't need to replicate them in every instance you will scale off, right? You can just have one for, let's say, 1,000 neural networks, and you have like 2 decoders for 10 neural networks, and etc. And refactor. Yeah, it's not a really good joke, but like Jim Keller is vouching from what I have heard on like videos and podcasts. He's always saying, if you want to do a really good job at beating other companies, you should refactor the CPU design every 3 to 5 years. And he's talking about CPU design, right? If you think about it, probably you can refactor your like 2,000 lines of codes every like 6 months, right? It's not gonna be a huge job. But what it's gonna lead you to is when you're growing, having other people and coming and reading your software easily and working on different parts in parallel. And you'll be having easier time to do extra accelerations and extra features if you just keep refactoring your code base and adapting to newest, best techniques and newest, library versions. And last, really, really subjective slide is that basically a couple of advices. It's really important to invest in hardware for researchers because more hardware you have, faster it will go. You should really refactor your code. You should not have a legacy code for 1 year. Avoid relying on high-level OS libraries in production because they're gonna struggle here somewhere in the future when you have to scale. And neural networks are really intuitive. So if you have opportunity to do that, I mean, you could take some risk because you will get higher rewards. And last things, getting and then keeping talent happy is a key. And we could see that from many, many companies, like from small companies to really huge companies, right? Yeah, that's pretty much it. Thank you for listening. Q&A, yeah.
Thank you for your presentation. I have many questions. The first question, finally, did you use WAV2-VEC as a base model, right?
Yeah.
WAV2-VEC 2.
Yeah,
yes.
WAV2-VEC 2.
Did you compare your system with XLSR WAV2-VEC?
Yeah. Yeah, sorry, finish and I'll answer.
No, this was the first question.
Yeah, so Wave2Vec firstly came with like base model, which is 90 million parameter network, and came with XLSR 53, which is 300 million parameter network. Then on the second iteration, it came with XLSR 300, right? So you have 300 million parameter of network, which was trained not on 60,000 hours of data, but on 400,000 hours of data, right? And you have 3 versions of that. 300 million param, 1 billion, and 2 million. So yeah, we had to, of course, do a search for which is acceptable for our specific use case scenario, right? But that included engineering, research, and like business side as well, because you have to do you have to scale those huge models, right?
Okay. The second question: did you use language model on the top of STT?
Yeah, of course. So one of the most preferred ways to decode the ASR outputs right now is KNLM, N-gram language models, right? They're easy to optimize compared to transformer decoders. Transformer decoders are really, really, really expensive to use and really expensive to scale. So if you really optimize the KNLM, probably you'll be having, really good results and really on par results with transformer decoders. So.
Beam search is too slow in production.
Yeah, beam search is really slow, but you can do it in C++ and you can do it in parallel, right? So you can scale off on number of workers because CPU is pretty cheap compared to GPU. And if you use like multi-threaded optimized beam search on CPU, it's gonna cost you a really small amount of money to do that in parallel.
Okay, and last question, how did you resolve a problem with alphabets in diverse languages? Maybe did you do transliteration into Latin symbols?
Sorry? You're talking about alphabet, right?
Yes, alphabets and transliteration.
Well, not transliteration, but idea is that you should either stick to uppercase or lowercase, right? I mean, probably you could do both, but you could do casing afterwards as a post-processing step, right? And there are many different languages. For instance, like English is word-based. Japanese is not, right? It's character-based. So how do you optimize that? Well, the answer is, if the language you're looking for has a huge amount of characters, like probably like 20% of those characters are used like contemporarily, right? So they're not using all the characters. So, I mean, we're trying to keep the amount of characters to a minimum amount, like minimum viable amount. But what we're doing is basically, encoding and using all the characters, in UTF format.
And how many tokens as a result for all languages?
It depends on the architecture. For instance, for wave-to-wake, you have small amount of reduction, which is 320, right? And 320 reduction in the input sequence size doesn't give you really a good opportunity to use like byte level encoding or word piece, right? So probably you're better off doing like character level, right?
Yes, no, character level, but Armenian, for example, has own alphabet, and many languages is very different from Latin symbols.
Yeah.
And I think this is a problem because many tokens.
If you do character level, your number of tokens is your alphabet, right? So that answers the question, right? Pretty much. Oh, let's say like for Georgian, like we have 33 letters in alphabet, right? That's a token size if you use character level ASR, right?
Thank you.